Welcome to Algebra 2. This is section 5.6, the inverse of a function. All right, so we've been working with functions for a long time so far, and we've been able to solve for the output by having our functions expressed as y equals, our output equals, and then some rule that is based off of the x, the input. But what if we want our function to work in the opposite way? In mathematics, often we need to find out how to do something and undo something. So maybe it's not always the output that we want. We need to be able to manipulate and find the other variable. And in order to kind of clarify this, imagine this real world situation. So you're buying gas that costs $2.19 per gallon. We could say some function c of x equals 219 times x. That's the number of dollars, the cost you would incur by buying X gallons of gas. Well, what if instead we have $30 and want to know not the cost, but how many gallons? So here we need to set up a function that will have X as an output instead of an input. So this is just a very crude example of why we have inverse functions. We set them up so that they will give us the input as an output. I know that sounds really weird, but it's why we have it, to undo what we have our functions doing in the first place. All right. For a function to have an inverse, it must pass the horizontal line test. Okay, so when I have a function, I want to decide, does that have an inverse or not? I will look at a graph of that function. Let's say we have a parabola or something. And if I try and take the inverse, well, if I'm going to switch the role of input and output, x and y, then I want it to pass the horizontal line test so I know that when I take its inverse, that I'll only have one input to go with each output. So in this case, a parabola does not have a direct inverse. Instead, what we need to do is we need to restrict the domain in order to get it to pass that horizontal line test. So what we might do is we might say, okay, let's take that parabola, but only take x values greater than 0. That way, when we run our horizontal line test, we get one point where that horizontal line crosses. I know I have one input leading to one output only. Another term for that is one-to-one, meaning one input goes to only one output. Okay, so a really quick look at whether or not we can take an inverse right away. All right, so we got a couple slides here talking about functions and inverses. The first way that I picture when I hear the word invert, I think of like flipping. An inverted shape is a shape that's drawn upside down. It's been flipped. And that's what an inverse function does. It flips the roles of x and y. Again, it changes the idea of an input and output around. Okay, what this causes, if we look at a graph of a function and its inverse on the same coordinate plane, we get symmetry across the diagonal line y equals 1x. So if I were to have that, let's go back to that half of a parabola. If I graphed its inverse and I did the work the right way to find the inverse, I should see that inverse and the original function perfectly symmetrical across that diagonal line y equals x. And that makes sense because if we're flipping the roles of x and y, flipping the x's and y's around, then we should see them reflecting across the place where they're equal. Secondly, the other big topic of inverses is that they undo the work of an original function. So if we go back to our gas example, having gallons as an input and cost as an output, with our inverse function, we would have gallons as an output and cost as an input. So again, just switching the roles of our input and output. Now, the way we show that through algebra, the way we prove that functions are inverses of one another is it's called a composition of two functions. So you can see I'm taking f of g of x. So f of x and g of x are two separate inverses. So think about what's happening when we do f of g of x. We have our ultimate inside. We have an input x going into this function g, and then the output of that, g of x, is going into function f. And if that ends up coming out as the same thing it started off as, that means it goes into the machine, into function g, gets worked on, goes through the second function, the second machine f, which undoes all the work of g and leads us back to the same thing we input in the first place. So it's a nice check, a nice way to just plug in values and confirm that we have inverses or not. All right, so example 1, it says solve where y is equal to f of x, solve that for x, then find the inputs when the output is -3. Okay, so ground level idea here of an inverse, switching our inputs and outputs, just like our gas station example. So if this f of x really means y equals -2/3 x plus 1, and y is our output, it says to solve it for x. So I would first subtract 1 from both sides. Then I have the quantity y minus 1 equals -2/3 x. Then I would want to divide away -2/3 to finish solving for x. Dividing by a fraction is the same as multiplying by the reciprocal. So I would multiply both sides by -3/2. So x, that was my input, it's now kind of taking the position that y did initially. It's the output now. Or at least it's in the place where our output was. And we've kind of worked our way backwards through all the operations so that I can plug in a y value, what used to be an output, and then I'll get an answer for x. So it says evaluate when the output is -3. So that means my x, if I plug in an output of -3, it's going to be -3/2 times -4, I get 6. And if I wanted to check my work, let's see what happens if this x, which in our original was an input, let's see what happens if I plug in a 6. Do I get a -3 for an output? -2/3 times +6 is -4 plus 1. Sure enough, that's a -3. So it checks out. Let's try number 10. So here my y value is 2x to the 4th minus 5. Well, y is an output. Let's solve for x. I want to add 5 to both sides. That tells me that y plus 5 equals 2x to the 4th. If I want to keep solving for x, I'll divide both sides by 2. And then I finish solving for x by taking the 4th root of both sides. Okay, so here's where we're tying in this radical idea. How do we undo a power? Now we have the radicals to do that. So my x value is actually equal to the 4th root of y plus 5 over 2. Okay, now taking the 4th root of both sides, it's like square rooting both sides. It really does mean that I could have a plus or minus situation on my hands. So I want to be careful here and think about what 2x to the 4th would look like graphically. Okay, well, an x to the 4th kind of looks like a square root function where it goes like this. And obviously, we've shifted it around a little bit. It's going, or it's twice as tall, and it's 5 units to the right. But it's generally taking that shape. So I want to think if my inverse, I've essentially found the inverse, is going to have that type of symmetry, then I'm going to have to restrict the domain because this plus or minus is giving me a parabolic looking thing. To get that symmetry, I can only keep this so long as x is greater than 0. Okay, so that's one of those cases where our domain comes into play. Another way of thinking of it is I only want the positive version of these x values. So instead of having plus or minus, I just want the positive. I want it to be 1 to 1. So let's find the input. When the output is -3, I want to solve for that x. It's going to be the positive 4th root of -3 plus 5 all over 2. That's the positive 4th root of 2 over 2, 1. It's just 1. So I'll check that work. let's see, does x equal 1? Well, if I plug that into my original, 2 times 1 to the 4th, that's 2 times 1, and then minus 5. Sure enough, that's a negative 3. So the output is negative 3 when that input is positive 1. Anytime we can break these functions down, instead of saying x's and y's, sometimes that's a little bit unclear. Inputs and outputs are a nice way of solidifying what they mean. All right, next example. Here we want to find the inverse and then graph the function and its inverse. Well, to find an inverse, we're going to do exactly what we just did. Often you will see the inverse of a function, like here we're starting off with f of x. F to the negative first power of x means the inverse. It doesn't mean 1 over like a negative exponent typically would, but it's understood to mean the inverse. So let's make a little note. F to the negative first power of x means f inverse. It's a different type of function, f inverse of x. Okay, so I still want to see this as a y, as an output, because I want to flip the inputs and outputs. And it actually is exactly what you'd expect. If I want to flip the roles of x and y, I'm going to take this equation that's y equals negative 4/5 x plus 1/5, and I'm just going to switch the roles of x and y. I'm just going to swap those variables out. Okay, so now we've flipped them. Our input has taken the place of the output, and vice versa. Now we're just going to solve it for y. So we're going to subtract 1/5. We're going to multiply both sides by negative 5/4. Multiply by the reciprocal. We've got y equal to, if I distribute this negative 5/4, I get negative 5/4 x plus 1/4. And that is my inverse function. So what's helpful about having a new name for this function is that now graphically is much easier because my x's still mean places on the x-axis. I don't have to concern myself about flipping the inputs and outputs like we did in the last examples. So let's graph these two and see if they show the type of symmetry we want them to. So the original function, we'll graph that one in red. I'm up at positive 1/5, and my slope is down 4 to the right 5. And then we can connect those points, and if I had a straight edge, I would use one. I want to make a straight line graph as clean as possible so we can, without a doubt, see that symmetry. Then my inverse function. Here I'm going up 1/4, and that slope is a negative 5/4, so I go down 5 to the right 4. There's another point on that line, and I will graph that one in. Again, using a straight edge if I had one. And then let's just rough in the line y equals x. Do we see symmetry? And again, if I'd used a straight edge, we would definitely see that symmetry happening there. We know we've graphed it, those two functions correctly. Another nice way to check is in the calculator, you can type the original function in as y1, and then you can type in your inverse function as y2, and that will graph it with much more precision. You can see that symmetry a lot better. Let's try another one. For number 28, here you can see we've got f of x, or y equals negative x to the 6th. And we would graph that using our calculator table maybe. But remember, we're only keeping this for x values that are greater than 0. So even though the graph itself, let's see, 2 to the 6th is 16, so we'd be way, or 2 to the 6th is 64. We'd be way, way down. Very, very steep looking graph. Like so. Even though that's what our negative x to the 6th graph would look like, we only want to keep it when x is greater than 0. So I'm only keeping the right half of that. And I want to keep that in mind as I'm finding my inverse. So let's flip the roles of x and y. And what would we do? We'd multiply both sides by negative 1. And then we'd take the 6th root of both sides. to cancel out that sixth power. So y equals the sixth root of negative x. Now you may be thinking, oh, a negative under an even indexed radical, I can't allow that. Well, we can. As long as the x's are negative, then I'll be taking a negative negative underneath. So here, as long as I allow x inputs that are purely less than or equal to 0, then I'll be having a negative negative or a positive happening underneath that radical. All right, so if I graph this, again, we'd use a calculator table or something. This is our inverse function, you know, all of this up above. Then, sure enough, here's what we see. Again, I'm just using a table for this. Our graph would look like this. And do we see the type of symmetry across the line y equals x that we want to see with inverses? Sure enough, we do. So we can confirm with the graph that we do have the correct inverse. Okay, our third example, here we want to determine whether or not we have inverses or not. Then find inverses. Okay, so for 38, here, oh, parabolic charades, right? You know, we've got a transformation. It's just a regular square root, but 6 units to the right. So it looks like that. Does that pass the horizontal line test? If I were to put a horizontal line in, sure enough, yes. Every horizontal line I would draw in would only intersect that graph at one point. It's a one-to-one function. We can find the inverse. To find the inverse, I flip the roles of x and y. And let's solve. I would square both sides, and then add 6 to both sides. That is my inverse function, f inverse of x squared plus 6. Put a little equal sign in there. All right, so x squared plus 6, though, that is a parabola. So I'm going to have to restrict the domain, because if I were to draw in a parabola that's up 6 units, that is definitely not symmetrical to the like one loop I see on my square root function. So I need to make the claim that I can only have this inverse when x is greater than or equal to 0. Because I don't want the left part of this parabola, I just want the right part in order to have that symmetry that we want. Okay, so the graphs do tie in, and your calculator can be a great help to graph these accurately and quickly. Number 42, here I've got a cubic function. It's twice as tall, and then 5 units down. So I'm just going to rough in a quick sketch of that. We could use a calculator table to make a much more accurate one. But this is what it looks like. Does it pass the horizontal line test? It absolutely does. Everywhere I would draw a horizontal line, I would only intersect that graph once. So we're good to go. Let's flip the roles of x and y and solve for y. I would add 5 to both sides. I'd divide both sides by 2. And then I would take the cubed root of both sides. So this cubed root of x plus 5 all over 2, that is my inverse function. Okay, and what's that telling me? Well, I could use the calculator to check. Oh boy. I just noticed that I graphed this function. I graphed a cubed root instead of a cubic. Oh boy. It's been a long week, people. All right, so we are down 5 units. It is still twice as tall. But the cubic function actually looks like this. Then our cubed root function, it's showing a typical cubed root, but it's going half as fast, and it's also shifted to the left 5 halves. Okay. Or sorry, also shifted to the left 5. So it would be over here, going half as fast. There is that cubed root function. And we can see that we don't have to adjust our domain because we do have the graphical symmetry. There we go. again, calculator table would really help with those graphs. That would have helped me out a lot if I would have just taken the time to use a calculator table instead of freehanding it. Example 4, determine whether or not the two functions are inverses. Well, this is where we are going to test f of g of x. Meaning, if I run an x value through function g and then through function f, do I get x alone as an output? Well, take a look at what this means. I'm taking the entire function g, and that is my input to function f. So instead of x minus 3, I've got 4x plus 3 minus 3 all over 4. So you can see that I'm just changing the input into function f. Well, let's see what that does. In the numerator, I can combine like terms. That plus 3 and minus 3 cancel each other out. Oh, and then I have 4x divided by 4. I get right back to x, the original input, into all of it. Let's also confirm that it works the other way around, g of f of x. So if I plug all of function f into g, do I still get x as an ultimate result? Well, instead of 4 times x, I've got 4 times x minus 3 over 4, and then plus 3. Well, if I have times 4 and divided by 4, those cancel. So I'm left with x minus 3 plus 3. Hey, and we can combine like terms now. I get right back to x. So f and g are confirmed to be inverses, because plugging one function into the other results in just getting the ultimate input x. Right. And our final example, a word problem where we have to use inverses to solve. Here we've got an exercise band, okay, that relates the total length of the band when it's stretched out to how many pounds of resistance it applies. It says find the inverse, and then use it to find what length provides 19 pounds of resistance. So usually pounds of resistance is an output. We want that as an input. So our inverse, I'm going to reverse the roles of R and L. Okay, flip the roles of my input and output. Okay, let's solve for R. Okay, I'm going to change my variables here. I don't like that. I'm going to call my input the length x and the output the resistance y, just because if I flip R and L around, it's not going to be as clear as if I do it this way. So let's see, if I have y equals 3/8 x minus 5, if I flip the roles of x and y, I would add 5 to both sides, then multiply both sides by the reciprocal, 8/3. So I'd find that y equals 8/3 x plus 40/3. Okay, and that's the same thing as my inverse. Okay, so that inverse, it used to accept an input of length, and it would give us an output of resistance. Well, now, this new function we made takes resistance as an input, and then it will output the length as an output. So it's working in reverse. All right, so find the inverse and use it to find what length L is going to equal an input of 19 as far as resistance is concerned. So L equals, let's see, 8 times 19, 80 and 72, 152. L equals 192 over 3. It should be divisible by 3. It looks like a 60 and a 4. So that length is 64 inches. We do have units. We want to describe them. We're finding a length. Be sure our answer has inches, that length measurement, as a unit. Okay, and again, just to explain why I chose to replace with y and x, Y and X are like your typical input-output variables. If I had left those at R's and L's, I totally would have been able to do this problem, but my final answer would have changed what those represented. So then all of a sudden in my problem, L that used to represent an input, it would still be taking the input place, just like X still had the input place. It would make it a lot harder to interpret how to use that inverse function. So when in doubt, if you have a situation like this, recognize what your inputs and outputs are and use X's and Y's. I think it helps clarify what the process is trying to have you do. But that does it. That is section 5.6. Here is a look at your assignment. Again, remember, EOO means every other odd.